All right, and we are back and we are going to go through our problem set 6 solution videos. So we're going to set up our coordinate system here, X and Y. We have our material and we'll fill in those properties. And let's go ahead and we're going to write out our fundamental equation. X equals positive 5 times 10 to the 3, because Q of X is our distributed load, so it's just that. It's distributed all over our beam, so we're good to go. What are our boundary conditions? They are symmetric, meaning that Y at 0 is going to be equal to 0, which is going to be equal to our displacement of our beam at L. Excuse me. Bugs here. Y prime of 0 is equal to 0, which is equal to Y prime at L. And we can solve for the rest of this now. So let's go ahead and pull up our little notebook here that has our beam bending. Let's go through here. So it's a polymer, so that's 1 gigapascal. We also have our thickness of our beam. Our beam length is going to be equal to 76 millimeters. The thickness, which is our height, is equal to 2 millimeters, and then our width is equal to 5. We have our moment of inertia here, and we can go ahead and set this up as, again, 5 times 10 to the 3 right here. And then Y of 0 equals 0, and then luckily these match our boundary conditions. So fourth order ODE, we need 4 boundary conditions here. We'll solve it. And then now we gotta wait to see what will be our solution. All right, something that's a little bit more straightforward because we don't have to deal with that delta function. So this is our solution. Let's see if it makes sense. Good is pointing up. That's fantastic. So, and we see our boundary conditions match. So determine the maximum displacement. So we actually have a maximum here. So we want to find, instead of find maximum, I want to find, or find minimum, I want to find maximum. And it looks like probably around 0.04, but I don't think we need to help it out too much. And 0.13 at 0.038, excellent, looks correct. So we have our value here. That's our maximum displacement. Determine the value of maximum stress. So remember, for stress, we need to relate that to our moment of inertia, which is that second derivative. And we can see, and actually see where that makes sense. We're going to find the maximum again, because that seems to be true, the largest value, because our stress is going to be maximized where our bending moment is maximized. So we can take this value here and plug it in as our equation for stress, remember, is minus bending moment. H over 2 is just basically our Y over I. So we can see here, and that does make sense, because if we look at our deflection at this here, at the top of the beam, actually, if we look at this right here, right at that location, we should be in tension. Or excuse me, the top of the beam is actually going to be in compression. If we were to plug in minus H over 2 here, then this would become a positive stress. So, and you can kind of see where the tension and compression is there. So excellent. We've got this. We've found the value. So the black curve is our material. Will this fracture? So what is our stress that we see here? So this is about 722 megapascals. So yes, we are indeed going to fracture. We're probably basically an order of magnitude larger than this. So that is it for that problem. So let's go ahead and see. Are we good here? We're good. We're good. Fantastic. All right, let's look at the next one. So we have a ceramic beam now. So we have an X and a Y location again. We're going to have to write out E, I, Y, 1, 2, 3, 4, X. Now it's going to be equal to, I'm going to start here as our origin. Now it's going to be equal to minus 17 times 10 to the 3 newtons, Dirac delta, and that load is applied at X minus L over 3, plus 4 times 10 to the 3 at basically this value, Dirac delta at x minus 4L over 5. We also have that our displacement at 0 must be equal to 0. This is kind of a funny problem, but we're just going to keep it the same. Y at 0 equals 0. Y at L also equals 0. Y prime at 0 equals 0. And then there is no restoring moment at that pin. So this is equal to 0. So let's go ahead. Let's go back up. And then I want to plug in the actual values. Let's go ahead, quit our kernel. Quit kernel, local. Good, good, good. You can put this one out there. Excuse me. Just taking a sip. Quitting. Oh, here we go. All right, now we're moving. So we are told that we're dealing with a ceramic beam, so this must now change to 300. Length of 79 centimeters, so times 10 minus 2. Thickness of h is now equal to 0.45 centimeters, and then our width is 12.8 centimeters. Minus 2. Okay, we're going to go ahead and scroll down. So I'm going to scroll down here, and we are going to go, I'm going to just type this in. So minus 17 times 10 to the 3, oops, minus 17 times 10 to the 3, times Dirac delta, Dirac delta x minus L over 3, plus 4 times 10 to the 3, times Dirac delta of x minus 4L divided by 5. That's our function. Y of 0 equals 0, y prime of 0 equals 0, y of L equals 0, y double prime of L equals 0 because of that moment. And now we can go ahead and start to figure out the rest of the expressions. This is going to get a lot nastier because we have that discontinuity. And we can paste that into here, shift enter that. We can go ahead and put that in here now. And again, it's a little silly, but kind of makes sense here. In terms of our beam and the bending, we're going to now find the minimum because that's going to be our displacement. Find minimum. And we see it's at 0.36. Okay, we see that. Fantastic. We can get our moment. And we don't have to copy and paste that in here, thankfully. We can find where that moment is maximized. And so we're going to do it, actually, we're going to do find minimum. And we have this value here, which is going to be the largest value. And we're going to plug that in at this location here. So now in this problem, we're going to see that basically if we look at our deflection here, if we look at basically the way it's kind of in negative curvature right at here, so that's going to actually give us this, again, the top of our beam will be in tension. And again, it's a significant value. So let's go ahead and look with what we've got here. Can I have this stress exceed the yield stress? The beam can't displace more than 15 centimeters. So the displacement, 15 centimeters, we're okay for the displacement. So that's fine because we're less than the 0.15. The stress exceed the yield, the material's the red material. So we're in the gigapascal range. So red, yeah, so we're failing on this yield stress. So boop, boop. Oh, that's not good. All right. So it will not work. But, all right. So we did some dynamic contest. We forgot to save the results, but remember the acceleration times on material A, B, and C. A had a acceleration time this, B here, C, and then D is infinite. So what are we saying here? Draw the curves, storage and loss modulus. The curves for each material indicate those curves with time as the x-axis. So let's go ahead. So we have, I'm going to go ahead and label, I'm going to use basically, this is going to be for storage, so G prime, and then, oops, let me undo that. dash is going to be my g double prime. We need time on this axis, so I'm going to actually write down. So this is going to be 2,000 seconds. This is going to be 78 seconds, and then this will be 32 milliseconds, not to scale, obviously. I'm also going to put A is red. I'm going to put B. I'm going to do this as C, and I'm going to do this as D. So let's keep with D first, because D is infinite, meaning that basically the relaxation time takes forever to respond. So it's not instantaneous, it's hard to rearrange. So basically it's behaving only like a solid. So it's going to be like this, will look like this. If the relaxation time was 0, it means it it responds instantaneously. That would be like a fluid. Excellent. So at long times, we know we behave like a fluid. So C has that relaxation time as 2,000 seconds. So at very, very long time, so I'm basically here, we are solid here until we cross over here. And then this one would be like this. And then for here, B has that very, very, very small relaxation time. So basically at long times, we're going to, in very, very short times, we're going to behave like a solid. So we look like this, and it could be look like this. Then we're fluid right after that. So very, very fluid-like response. And then let's go to our red, the same thing here. So we're going to look like this, and then the red's going to look like this here. Fantastic. All right, what does the problem say now? Label blah, draw the DMD curve, be sure to label with frequency. So if this was frequency now, so this is time. If this is the frequency axis, we would have very, very, very high frequencies here and low frequencies on this side. And you can just do the inverse. So really, actually, here it would be 1 divided by 32 milliseconds, 1 divided by 78 seconds, 1 divided by 2,000. And you can see how the frequencies are getting actually smaller there, and high frequencies on the left side. Fantastic. Good. C. Temperature and strain rate. So temperature will look the same as time, and strain rate will look the same as frequency. Nice. Done. Which of these materials are viscoelastic, which are solid, which are liquid, which viscoelastic is most liquid, most solid? So we've said this already here. So D is a solid. A, B, and C are viscoelastic. The most fluid is going to be B. The most solid will be C. Yeah. Excellent. And then in the middle is the other one. Turns out we misread X with the relaxation frequency of infinity. So again, this is actually a tricky problem. Relaxation frequency of infinity. Frequency, or omega, is going to be, or actually, I'm not, typically frequency, or F. F is going to be 1 over our relaxation time. So basically that means our relaxation time, tau, is going to be 0. So if it was infinity. So we're going to have F is equal to infinity. So our tau relaxation time is going to be 0. So that would, again, basically be a fluid, an instantaneous response. What are we asking to do about this? Okay. So now this obviously would be our fluid material. And if I'm just going to create a new, I'll just make it yellow. So it would look very similar to actually, I'm not going to do that. I'm going to do this, but I'm going to make another curve. Let's just do this. So now it would be flipped. It'd be like, if I'm a fluid, my loss is always higher than the storage modulus. So that's it. Fantastic. If you can do these problems, you're going to ace that exam. So thanks, and see you to the next video. Bye.